I will show you now 3 ways that are rather code efficient to plot your results. And I think this is something that you all are looking for. There are many ways to do that. And there were many cool and clever people that develop packages for us to make it code efficient. And I will show you some. And while we do that, we will also remind ourselves how to interpret regression coefficient, because this is not that trivial. Okay. So one really, really quick and dirty way how to evaluate the population level effects of your model comes with the conditional effects function, right? So if we run this, and I've already ran it here, it's on line 335, we get 3 different plots, okay? Let me make that small for you. So first of all, we get a plot for the effect voicing versus voiceless, right? So some people might think of main effects, but we don't want to really dive into that. What the really handy aspect of this function, it plots it immediately into the scale of the data, right? So in this case, in probability scale rather than in log scale, that makes the interpretation easy. And it's kind of a quick and dirty way to look at rough ballparks of where our parameters lie, right? So here we see rough ballpark, voiceless, underlyingly voiceless sounds have been reacted to more accurately than to the ones that are devoiced, right? That are underlyingly voiced. The second one shows you the difference between the first occurrence of a stimulus and the repeated occurrence of a stimulus. And here again, you see rough ballpark, the repeated ones are overall, people are a little more accurate with regards to that, right? And finally, and this is probably the one what we're interested in, because we were interested in an interaction here, right? The last one is an interaction plot, and you should be familiar with these kinds of plot. You have in color, you have the repetition type, and on the x-axis, you have voiced versus voiceless, right? And you can see a couple of things. If you ignore the really, really wide whiskers here that indicate there's a lot of uncertainty, you can see in a pattern that kind of our brain would like to interpret in a coherent way, right? For example, you see overall, those stimuli that are voiceless are reacted to more accurately. We saw that already, right? So the ones that are voiced or devoiced, they're kind of closer to chance performance. But you see also an interaction here that is for the voiced ones, in the second iteration, people get a little better in perceiving them, right? And for the voiceless ones, they get a little worse, right? So you have basically a crossing interaction here, right? Now I want to remind us on how we arrive at this plot, okay? This is obviously nothing to do with Bayesian, it has to do with regression coefficients. And I want to just quickly look at the model output with you guys and think about it a little bit. And we really just want to look at, let me make that a little bigger. Oh, that's a mess. Okay, there we go. Let me see where we can make it a little better. Okay, there we go. So let's look at these 4 lines here, right? And just look at the posterior mean here, the estimate column, right? Just to remind ourselves. So in this case, our reference level is voiced and the first occurrence of a stimulus. That's our reference level, right? And for that reference level, our model predicts a posterior mean of 0.01. Let's, for convenience, just say 0, right? What does 0 mean? 0 means in probability space, 50%, coin toss, chance, right? And we can see that with the red dot in the voiced column here, right? That is our intercept, right? Now the second coefficient tells us if you are at the reference level and you want to go to repetition type repeated, you have to add to the intercept 0.44, right? So if we want to go basically from this red dot to the whatever is a blue, green, blue dot here, we have to add 0.44 in logout space. So basically, we can use our p-logis function and just do that calculation, and we get this value here. Oh, sorry, I did the wrong thing. I told you about repetition, and I looked in the wrong row. We actually look at voicing. So we want to go from the red dot to the other red dot, right? From first occurrence voiced to second occurrence, from first occurrence voiced to first occurrence voiceless. You see this already confusing myself. So from the red dot to the red dot. And if we do that, if we calculate the coefficients together, we get a probability of 0.61. So that is that one up here, right? Now, if we're going to go from voiced first occurrence to voiced second occurrence, this is our second coefficient, right? So we add 0.16 to the intercept, right? So if you do that, we get something like 54%, right? This is this blue-green dot here, right? So we have covered how we get from the reference level to this red dot, from the reference level to this blue dot. What is left is how do we get to the blue dot on the right-hand side? That's where the interaction term comes in. Remember that this is how it is because of the way that the contrasts were coded or not coded, right? So we go with the default coding of R. How do we get there? Well, we need to go from voiced to voiceless, right? We need to go from first occurrence to second occurrence, and we need to go diagonally to that term that we have not reached yet, basically. So we add all of these together, right? So we have 0.44 for voicelessness, 0.16 for the repeated repetition, and finally, minus 0.22 for interaction term. And that's where we end up with 0.59. In case you were confused about the regression coefficients, and they are confusing at times, especially when you operate in a non-intuitive parameter space, this is what it is, right? And we just basically, by hand, double-checked the coefficient against this plot that we automatically generated with the conditional effects function, right? So that seems to be roughly in the same ballpark, right? So this is always good for first quick and dirty look at the levels you're interested in, get a feel for both the position of the posterior distribution, but also its certainty, because we have these whiskers, right? Now, but this is all kind of way how we in the past did this, because frequentist approaches usually try to estimate one true parameter, but we get distributions, right? So we want to plot some distributions. So there are two things we can do, and that is personal preference and communicative intent that determines what we want to do. That's always true for data visualization. So there's one handy way with the base plot package to relatively quickly plot a so-called forest plot. So what you do is you first convert the model output into a matrix object, and then you feed it into one of several functions that this package offers you, and specify exactly which parameters you would like to plot, right? And we now go with all the predictors. That is our intercept, it's our it's correct voicing, voicelessness, repetition type repeated, and the interaction, right? And you then said, because this is a particular plot, you see that in a bit, that shades in a certain area within the posterior distribution, you specify a probability, right? And we have talked about that kind of classically, because we come from frequentist statistics, we usually use 95%, right? It's also kind of handy because it goes hand in hand with the 2 standard deviation rule of thumb. But it's arbitrary, right? And I want to demonstrate it here by just picking something that's totally arbitrary, 0.83, right? Now, if we do this, my computer is really working at the moment. So hopefully it will actually, let me see, plot it. It won't. I don't know, it's really heavily working at the moment. Maybe because it's such a big model object. Here we go. Right. So here you have on the y-axis, you have the 4 parameters. Right. On the x-axis, you have the log odds with 0 right here. Right. And then you have 4 posterior distributions for these parameter values, for these coefficients. Right. And you can see the dark blue line in the middle. That's our mean or median, depending on how you specify it. And then you have the shaded area that I specified as 83%, the middle 83% of that posterior distribution. Right. So this is a way to plot your coefficients. And some people, they just do that when they report their results. I don't personally, I'm not a big fan, and I can tell you why. It is because interpreting regression coefficients requires a lot of mental arithmetics, right? And you have to kind of put things together. What I want to see when I read a paper, which helps me better understanding what's going on, is to see actually the posterior distributions for the individual levels of the predictors that we look at. That's what we usually have little trouble with interpreting directly, right? So this is one good way, and a lot of people do that, and that's very useful and helpful. It puts possibly a small burden on the viewer that they have to basically, if they are interested in the actual levels, to make that that transformation in their head. So for more traditional plotting, and I don't want to go into detail here, it's not very involved. We use some very clever functions, the data grid and the add fitted draws function, to extract the posterior values for the different coefficients. And when you have coefficients, and we just did that by hand, right, in our head, you can add them up to create certain levels of that parameter, right? And if you do that, you just use ggplot. And in this case, we use a particular way of plotting data. You will see that in a bit. It contains a distribution, so a density curve, plus a standard points, plus a line that represents credibility intervals. So if we do this, we have the same problem as before. I don't know why it does not print it in my console. Oops. And you can obviously see that in the knitted HTML file and in your R Markdown file. And here we go. These are now the posterior distributions for the 4 levels: voiced, voiceless, and first occurrence and repeated occurrence, right? You see the distributions, and you see a dot that represents the mean posterior, and you see the 2 whiskers levels. And I think, please correct me if I'm wrong, it's 50% and 95% as a default. I'm not entirely sure, but you can also set that, right? So I give you a rough idea of what is going on. Okay. Joseph said it's 66 and 95. Yeah, that sounds good too. Like I'm not entirely sure what the defaults are. You can definitely change. Right, so this is that's at least how I like to visualize the data. But I also can show you so basically these are the posterior distributions, right? Now the posterior distributions are dependent on 3 things. They're dependent on your data, on your model, and your prior distributions. Because we've defined prior distributions very vaguely, let's just take them out of the picture for now. But the model specification is relevant, right? Basically, if I specify my model anti-conservatively, meaning, for example, I'm not taking into account different listeners, different speakers, different items, the posteriors might be more narrow, right? So it's always useful, and that's usually what I do in my publications, to plot the model estimates together with the data at hand. And I've prepared something for you here. It's also not rocket science, and you can just try to reproduce these plots with your own data and just plug them in. And they're not ideal, I can tell you why, but you can see now on the left-hand side, you can see the data plotted. And you might see that some of them are more transparent than others. That's because there are values overlap, right? Some values are exactly in the same spot, and that's why they overlap. So this plot, I didn't have much time to prepare it, is not ideal. You ideally want to tease them apart with jitter or with quasi-random geoms and ggplot. It's a little bit more involved, but all no rocket science. But this is nice because you can immediately look at, okay, what is the model predicting? And where are actually the data? And is it totally off or is it not, right? It gives you kind of a ballpark. So if your model is miserably specified, like you're totally off, you might actually see that if you plot these things together, right? We've already given you a lot of different ways to kind of evaluate how well your model has fit. But like at a later stage, maybe you kind of missed something. Here you might see if something is off. And I've experienced that coming to this late stage of plotting, realized, Jesus, something is totally off with the model specification because the data are not even in the same ballpark as the posteriors, right? So this is one way to do that, and there are obviously more sophisticated ones. But if you look into the R Markdown, that's not a lot of lines, right? It's not too involved. Obviously, you need to be fluent ggplot user and a fluent dplyr or like tidyverse user, but it's all there. If you find that useful, then please take this code and apply it to your own data. I saw, Stefano, you raised your hand.
I did, yeah. And there's a question. I'm not sure. Perhaps now it's the best moment, but perhaps it is. So I'm gonna read it for you.
Yeah.
Somebody asks, how does the model fitting procedure change in the approach that you're presenting us? Do you still test and remove effects or interactions which aren't useful? And if so, how do you do that?
I'm not entirely sure I understand the question. So basically, the model has not changed, right? What we did now is, so basically, if we go back to the forest plot real quick, I can show you what happens basically in the background to some extent. And this is something you can do with posteriors in Bayesian statistics. The intercept is the reference level, right? That was voiced plus first occurrence. Now, if you want to know the posterior of the second of the first occurrence in voiceless, you basically add the posteriors of the intercept to the posteriors of the correct voicing voiceless.
I think what they're asking is basically like sort of likelihood ratio tests where you compare a full model versus like a null model or something like that. That's what I gathered from the question. Yeah, and somebody else like was, you know, talking about maximal models and stepwise procedures. If I can just briefly say my point of view, I think we don't need that. I think you can just fit your maximal model and look at the estimates and the posterior probability distributions. And this idea of the best fitting model really comes from especially machine learning and some areas of statistics, but it's not the only way. But perhaps, Timo, you have a different opinion on that.
Yeah, no, it's a really complicated problem. And it's a really great question. And I understand why you're confused. And what Stefano just said is really crucial here. There are different ways of approaching statistics in the terms of what the ultimate goal is. Some people use it exclusively as a device to elaborate and to arrive at a decision, whether to act or not to act. And that means often accept or not accept a certain hypothesis, right? We can do that. Other people, and that is kind of the camp that is more placed in the machine learning crowd, they try to find the model that comes the closest to the generative process. So the process that made the data happen, right? And for that to arrive at such a good fitting model, and we kind of mix these things a little bit here because we kind of abandoned hypothesis testing for us, is you have to obviously you can't predict all the steps you need to take to arrive at that best model, right? And these model comparison tools are often used to arrive at that best model, right? But if you're in hypothesis testing land, and that's why I think a lot of people in psychology and linguistics had trouble understanding the discourse that happened between a bunch of statisticians, is that that finding the best generative model goes hand in hand with hypothesis testing. And this is not the case. Hypothesis testing in the strict severe, in the most severe form, should be a one-shot attempt to model the data and to test a certain hypothesis. As soon as you run a model, look at the data, change model specifications, and continue that process to arrive at a later stage at a test for your hypothesis, you've explored a lot of degrees of freedom already, which make the actual decision procedure according to a certain index, like the p-value, uninformative. Because the more you have looked at the data, the more possibilities emerged how the data can potentially show a meaningful, what you consider a meaningful pattern. And there are whole papers and books written about that. But that's not what we want to do usually, right? So successive model reduction or increasing model complexity is problematic from a hypothesis testing standpoint. Now we are kind of somewhere in the middle because at least Stefano and Joseph has just raised his hand. We want to estimate parameters, and then we want to have a model that is informative for that process of model parameter estimation. When there's no decision procedure to worry about, we don't need model comparison. But maybe Joseph has something to add.
I think that was actually very clear, and I think you hit it spot on. I just wanted to add that, well, we're talking about one perspective on how to do this process, but there are people that do it different ways. For example, I imagine that a lot of people here have used or are using the statistical rethinking book. And Richard McElrath, for example, does use an iterative model building process where it starts with a simple model and builds it up. And then they use information criteria to assess the model in terms of informativity. So there are other camps where people do it ways that are similar to like the nested model comparison type of model building that you see in a frequentist framework. We're just simply presenting another way of doing things. I think that you're going to see it out there, I guess is what I want to say. We don't want to give the idea that like Bayesian world, you don't do that anymore. There are ways of doing that. That's just not what we're promoting here.
Right, it's a whole, as Joseph said, it's a whole different topic, model comparison using Bayesian methods. We're not saying it's bad or in any inherently bad, right? We just want to caution you to quick solutions to a difficult and complex problem. Like even hypothesis testing is a complex process. And we know when we used LME4, we had a very, very elegant way to directly compare two models that have one model is the full model, the other one has one predictor removed. We get a nice little value that we can interpret. We get usually p-value or generated post hoc based on these values, and then we can make a decision procedure. Right? This will never be the case in Bayesian, that it's that easy. It's more involved. It's much more conceptually and technically demanding than what we have used before, right? So that is a downside if you want. But like I think Stefano said it earlier, I feel so much more in touch with what I'm researching on. I feel so much more, I feel I understand the quantitative system I'm looking at so much better. It's a very satisfying feeling, but I think also that makes me ask better questions and formulate better answers to the questions because I understand the system better. Right? And this is the upside that I see, and I think we all agree, Joseph, Stefano, and I, that this is a huge upside of this additional thinking, this added involvement. Any more questions directly related to this? It's obviously very philosophical, as you.
There's a ANOVA question. So also, as someone trained on ANOVA, I'm happiest choosing what I want to test ahead of time and interpreting the results, which is exactly what you're saying. Oh, sorry, that was not a question. It was actually a comment. So yeah, they say, you know, like I want to test something and I want to interpret the results. And this is exactly what we're saying, right? You don't try to find the best model, but you want to test ABC, you put in the model ABC and you see what happens with ABC, basically.
Right.
Sorry.
Yeah, absolutely. Yeah, that's great. Yeah. Anything else? I think then if there are no questions, or we can queue them up for later. I think the last step is now a little inference with Joseph again. Is that correct?